I am supposed to be speaking about in this. So, my part of the course is supposed to deal with orthogonality and inner products and singular value decomposition and so on. So, a lot of these are used a lot in these data science applications and machine learning and so on, and Professor Pranabendu in the afternoon will speak a lot about these applications. So, my own plan, at least initially, is more or less to recall some of the basic theory. I am sure a lot of which you must have seen in some form or the other, and with a little bit of emphasis on some of the computational aspects, from a pure linear algebra point of view, meaning how does one compute bases and things like that. The actual applications to machine learning and so on is something that Professor Pranabendu will talk about in the afternoon. Okay, so please feel free to interrupt at any point of time if something I am saying is not clear. So, let me begin by recalling the definitions which I am sure you are familiar with. So, inner products or inner product spaces. So, where does the story begin? As you remember, a lot of this is really based on our intuition in R2. So, I like to think of R2 as really being where a lot of these ideas evolved from, and in R2 the key thing that we often like to think about is this notion of lengths and angles. So, if I have got a point x comma y in R2, there is the angle that it makes theta with the x axis, and so the two things we know are the length of this vector. So, when you say length, I mean length of this vector, maybe we will give it a name v, is square root of x square plus y square, and the angle theta is essentially defined via the following relation, that it is just x. So, v denotes this vector here, cos theta is x over square root x square plus y square, sin theta likewise is. So, this is really where the story begins at some level, and what one does is of course to look at two vectors and try to understand what is the angle between them. So, if we had two of them like this, and let us give them names. So, this guy is a1 a2, let me not call it xy now, suppose its coordinates are a1 a2 and b1 b2, then the angle between them, in this case now which I will call theta, can be obtained by sort of looking at this outer angle minus this inner angle. So, as alpha minus beta, and cosine of that angle therefore is cos of alpha minus beta, and that is where our formula comes from for the dot product. So, this cos alpha cos beta plus sin alpha sin beta, and so that's just x, sorry, let us call it a1 times b1 plus a2 times b2 divided by so I have just used the earlier formulas for cosine and sine, and this is what we get, right. So, that is maybe the starting point. So, we see this familiar thing on the top, that is our formula for the dot product, and what it really helps us keep track of is in some sense the angles, right. So, the angles between vectors is what the dot product captures, and this is really what one generalizes to Rn. So, we say okay, we can take so the generalization to Rn is the following dot product. We just say given any v and w, we have the standard W is B1, B2, Bn, then the dot product V dot W. So, this guy on top which I did not really mention. So, if these two are vectors V and W, this is our familiar dot product. So, here the dot product is just summation A I B I, this is our standard dot product. Okay. Now, what does this give us? We use this primarily in Rn to study lengths. So, the length of V, which we usually now denote like this, the norm of V or the length is just defined to be the square root of V dot V. So, that is one thing that we get out of dot products, and in a sense we do not really talk about angles so much. Start new page. What we are usually interested in is instead just the 90-degree angle, that is often all we care about. So, length is one aspect, the other is orthogonality. So, we are also interested in the following notion: when is V perpendicular to W, and this we say is when exactly when V dot W is 0. So, this is in a sense our definition, we say V perpendicular to W exactly when the dot product is 0. Okay. So, there are two things that one gets, one is the notion of length and the other is the notion of perpendicularity. Okay. We can say more generally angles, but in a sense perpendicularity is all we usually worry about, okay, in the more general context. Okay. So, that is sort of what dot products are good for, and let me just recall the formal definition. If we have okay. So, if we have a vector space V with vector space is really just a structure only with notions of addition and scalar multiplication. So, it is a purely algebraic sort of object, and on top of this we really impose an additional structure, that of an inner product. So, let me say I have a vector space over, let us say, the field of real or complex numbers. So, let me not talk about more general fields. For me, I will always only be talking about R or C. Okay. So, a vector space is just this much information, and an inner product, let us define definition, an inner product on V is a function from V cross V to the field F with the following properties, that there is sort of linearity. If we have V1 plus V2 comma W, then the answer is just V1 W plus V2 W. If you have scalars on the first component, you can pull them out. So, this is for all C in coming from the field F, which can be real or complex in this case, and there is sort of a conjugate symmetry. If you interchange V and W, you are supposed to get the bar of the original, right, conjugate. Of course, if you are over the real numbers, then it does nothing. And finally, if we take V with itself, this is sort of the most important property, then the answer is always positive, greater than equal to 0, and equality holds exactly when V is 0. So, these are the properties of inner products which I think you must be familiar with. Okay. So, that is the positive definite defining property. Now, the standard inner product, of course, is the one which satisfies all these identities on Rn, and for Cn we just have to tweak it a little bit. So, the standard inner product on Cn just has V is a bunch of AIs and V dot W in the case of Cn is just summation AI Bi bar. Okay. So, of course, these are our usual definitions. Now, the key thing with these axioms is that there are many other definitions possible in various other contexts which also satisfies these axioms. So, for example, even on Rn, so the natural question is, in addition to this familiar inner product, are there other inner products one can define on Rn, right? So, is there, what do you think is the answer? Are there others beyond just this obvious one? How many are there? Maybe is another good question. Infinitely many, and sort of what is another example beyond this obvious one?
Some Ci AI Bi, some Ci positive.
If you multiply by a positive number, that will be
right. Okay. So, one obvious thing you can do is to just put summation AI Bi, just the standard formula, but then put some Ci's which are positive numbers. So, maybe I will, okay, Ci strictly positive. So, that again would satisfy these axioms, and but in fact you can also do more complicated things. You can also have, so here is another example of a non-standard inner product. In the case of R3, here's another one, maybe even R2. Say on R2 I have another option here. I can say V and W prime, this is the new inner product, is just A1 B1 plus 2A2 B2. So far it is like the earlier example, it is like Ci's have been chosen, but I can also have some cross terms minus A2 B1 minus A1 B2. So, even this, for example, is an inner product on R2, okay, and but that involves some checking. You have to check, for example, that it is positive definite, right. It is symmetric. If you interchange A's and B's, the right hand side remains the same, but positive definiteness requires some checking. So, if I take V with V, for example, with respect to this new formula, it is A1 squared plus 2A2 squared minus minus A2, sorry, minus 2A1A2, correct. So, that is A1 squared, A2, 2A2 squared, 2A1A2, and we sort of have to see if we can complete squares in order to show positive definiteness, and here you can, right. So, this is in fact going to be positive and 0 exactly when A1 equals A2 equals 0. So, there are many other formulas possible, and we will sort of see later on how one can write down all possible inner products, for instance. Okay, but this is just on Rn itself. Now, one can actually try and do more exotic stuff. So, here are more exotic examples. I mean, I say exotic, but not really. These are all very standard sorts of examples, especially with machine learning and data science applications. Here is a very important example. So, this is where instead of Rn, the vector space that you are considering is actually a space of matrices. Okay, so, here is my vector space V. I am just going to take the set of all m cross n real matrices for now. You can similarly do it for complex also. So, if I take the set of all m cross n real matrices, I could think of this as a vector space over R as well as what, just R mn, right. I have got mn coordinates, mn components in the matrix. I just think of them in some sense as one long vector of size mn, except it is arranged in this matrix form, that is all, in terms of rows and columns. And so, here I have the standard inner product, right. So, I am just going to take the same standard inner product on this space, except I will just try to see what it becomes when I try to rewrite it in matrix notation. Okay, so, I have two matrices A and B, and what is the standard inner product? This is just summation each entry of A multiplied with the corresponding entry of B. It is actually a double summation over both I and j, I going from 1 to m, j going from 1 to m. Okay, so, nothing new at this point, but here is an important way of thinking about this. I can rewrite this as A times B transpose, Okay, so imagine what is A. A is an M cross N matrix, B transpose becomes an N cross M matrix, and when I multiply the two of them, A times B transpose, it is an M cross N matrix. So, the final answer is M cross M. And what are its elements? Well, it's, I mean, I want trace, so I want to know what are all the diagonal elements of A B transpose. Now observe that that is exactly the inner sum here. So if you rewrite this as I going from 1 to M, and you look at what this entry here is, it is the ijth entry of A times the jith entry of B transpose, right, and J is the guy you are summing over. So this fellow in the middle is exactly what you would get if you take AB transpose and try to take the ith element of AB transpose. So it is the ith diagonal element of AB transpose, and I am going to now sum over I. So what I finally get is nothing but trace of AB transpose. Okay. Likewise, I could do it with the complex numbers as well. So let me just mention the thing as well for completeness. So if I take instead of V, I take V prime, which is M cross N complex matrices, and take the standard inner product on this space, then it has got this nice expression. So the standard inner product is summation Aij Bij bar is nothing but trace of not AB transpose anymore, but conjugate transpose, which is something that we usually write as star. So this is trace of AB star, okay, where B star is the conjugate transpose matrix of A, of B, sorry. Okay. So this is just standard inner product except rewritten in matrix form. Okay, and this is an important this sort of an important matrix in some sense, an important formula, because this appears a lot in actual applications. Okay, so this is one. The other example again of interest from an applications point of view is the space of functions. So function spaces again have inner products. So if you take V to be the set of all functions from, let us say, 0 1 to C, let us say continuous functions. So continuous complex valued functions on 0 1, then the usual inner product one thinks of on this space is given by the integral fx gx bar dx, okay, the integral is from 0 to 1. And again this is, you know, the integral is well defined, because f and g are continuous functions. You can always integrate them on a compact interval here 0 1, and again the interesting thing here is in proving to show that it is a, you know, it is a well defined inner product, the in a sense non trivial part is only the positive definiteness. So it is really what happens when you put f equals g, it is fx into fx bar, so it is a modulus of fx square dx. So of course the answer is positive, that is all right, because the integrand is positive, but why is this 0 if and only if f is 0? That becomes an important thing, right? And that happens because of the following reason. So now this is all right. Suppose it is 0, then I need to show that f is 0. Okay. So that sort of comes from the following: if I have got a continuous function on the interval 0 1, and you know, look at mod fx square, that is also a continuous function, it is a continuous non-negative function. If it takes a positive value, if it takes a non-zero value at some point, then because of continuity in some neighborhood of that point, it is still, you know, it is bounded away from 0. And so even if it becomes 0 very quickly afterwards, there is definitely going to be some region which will contribute to a positive area, right. I mean, I am not giving a formal argument here, but just trying to say that this continuity is very important in this definition. Only when you take a vector space of continuous functions can you claim that this zeroness can only happen when f itself is the identically 0 function. Okay, this again is an important inner product on this space, the interesting thing here is that this vector space itself is infinite dimensional. Right? This is not a finite dimensional vector space, this is infinite dimensional. Okay, so this is an example of an infinite dimensional vector space on which you have got a very naturally defined inner product. Okay, so I am hoping you have seen all this in some form before. Now let us move on to other important properties of inner products. So the next thing that I want to talk about is a relationship between the inner product itself and the norm. So let me just dwell a little bit on this business here. So in a sense there are two things in the picture. On the one hand we have inner products, and given an inner product we obtain a norm from it, right. So norm, remember, is just the notion of length alone, whereas inner product is slightly richer. It's got in some sense notions of length as well as angles, or length and perpendicularity. So if I give you an inner product, if I know how to compute inner product of every pair of vectors, then from that I can figure out what the norm of every vector is. It is given an inner product, given the inner product values, I can find all the norm values. How do we do this? Well, that is just definition. What is norm of V? By definition it is inner product of V with itself square. So that is easy, nothing to do there, right. But what is interesting is that the norms also determine the inner product. In other words, suppose I knew what the norm of every single vector in my vector space is. If I knew norm V for every vector, then okay, so let's continue. So the point I want to make here is that the sort of the converse is also true, that if you knew the values of norms of all vectors, from that you can deduce the values of inner products between pairs of vectors. Okay, and this is, well, again just the following formula. For instance, if I am in a real inner product space, so this is over a real inner product space, we know this trick of writing. So if you actually compute this, V plus W norm whole squared is just V plus W, the inner product. So if you sort of look at what this will become, this will be VV plus WW plus 2 times VW, and the other guy, the second term, will be the same thing, except you will get a minus 2 VW. Okay, so everything else cancels, so this will sort of cancel with these terms, and you will be left exactly with a 4 VW divided by 4, right. So this is sometimes called the polarization identity, and there is likewise a corresponding thing for the complex case. If you are over the complex numbers, then you just have to do a little bit more work there. You sort of also have to throw in some i's and so on. So V plus W squared, V minus W squared alone won't do the trick, because one of them will have VW, the other will have WV, and there some will not give you VW, it will just give you the real part of VW. So then there is some i's to be thrown in, so it is something like this. So you sort of have to do a little bit more, but at the end of the day you can still manage what you want, which is to express the inner product purely in terms of the norms. Okay. So this sort of this idea is important, that somehow you can get one from the other, okay, and there are variations of this idea which are used in various places. Okay, so broad philosophy here is knowing all lengths tells you all angles, knowing all the angles or knowing all inner products tells you all the lengths. Okay, but this is just for anything, yes, because it just uses the definition of the norm, right. You just start with this property that norm is equal to square root VV, This is all you are using. Norm square is VV, and then just if I have an infinite dimensional vector space on which I have an inner product, these formulas will work.
Suppose it has the inner product.
If it has an inner product, yes. I am not saying that if I only give you a norm, I will be able to get an inner product from it. Right? So that is the point that I want to make next. So this is, I am assuming I am talking about an inner product space. See, all this thing which I told you is assuming that I have V and an inner product on it. Then I am asking, are norms and inner products calculatable from each other? I have an inner product to start with. Okay, now what you are asking is the following question: suppose I did not have an inner product to start with, can I just look at vector spaces in which I only have a norm defined, I do not have an inner product defined. Okay, and that again is useful for applications. So let me state what that is. So this is sometimes called normed linear spaces, not an inner product space, but just a normed vector space or a normed linear space. It is the following: I have got a vector space and I only have a notion of length. Okay. Now what does a notion of length mean, right? What is the length function or what is the norm function? So let's define this, but let me not use the same notation as before, because then we are probably going to get ourselves confused. So let me call the norm function as n. So a norm on V is a function n from no longer from V to V, but just from V itself, right? And the result, the output goes to the set of non-negative real numbers, irrespective of what my field was. See, the field can be real or complex, that does not matter, but the norm, which is supposed to be some kind of length function, right? The norm is only going to be positive real value, it is not going to have complex numbers as values. So what is a norm? It is a function from the vector space V to the set of non-negative real numbers, satisfying some axioms such that, firstly, norm of, if I take a vector V and I multiply it by a scalar C, then the modulus of C just comes out for all scalars C. So it just says if I sort of stretch a vector by some amount, the norm of that result will also multiply by that same factor, right? This is dilation or shrinking. So that is one property. The other important property is norm is 0 if and only if the vector is 0. So this is norm of a vector is 0. Only the 0 vector is allowed to have 0 norm. So this is like positive definiteness in some sense. And finally, this is the triangle inequality, which says if I have two vectors V and W, the norm of the sum is the less than or equal to the sum of the norms. So I have vector V, vector W, V plus W is sort of this guy here, then the norm, the length of that diagonal of the parallelogram is less than or equal to sum of these two lengths. So you can think of this also as having length W. So this has length norm V, this has length norm W, so this is just the usual familiar triangle inequality, and this is how we axiomatize it. We say if I now have an arbitrary abstract vector space, a norm on that space is just some positive real valued function which satisfies the triangle inequality basically, and of course the other two axioms. Okay, and there are of course many examples of norms. The obvious choice is if you had an inner product, then from that we have a norm, right? So what are examples of norms? So here are examples. Is if I had an inner product, then I can get a norm from it. If V is an inner product space, just shorten it to IPS, then Vn is a normed linear space where n is the norm that comes from the inner product, where n is defined as square root of V V, right. So, this is the obvious way in which you get norms starting from inner products, but there are also many norms which do not come from inner products, okay, and this is an important distinction to keep in mind. So, the other examples which do not come from inner products in this manner are norms like, for example, on Rn or R3, maybe I will just say Rn. So, if I have a vector a1, a2, an, I can define the norm of this vector to just be the sum of the AIs. Okay. So, the usual norm which comes from inner product will be the sum of the squares of the AIs and square root of that, right, but I can just say take the sum of the modulus of all the AIs. This turns out to also satisfy the triangle inequality, right. The other choice is the following: I can take in fact just the maximum of all the AIs, maximum of modulus AI. Okay. So, this is what we usually call the L1 norm. The first thing I wrote out is the L1 norm, the second thing I wrote out is the L infinity norm, and so on. We have more general LP norms. It turns out that these guys cannot come from inner products, okay. That is a very interesting thing to check. Maybe we will put that as part of the tutorial, which is that this norm here, this for example, this cannot come from an inner product. In other words, maybe I will just say exercise, we will do this in the tutorial. There does not exist an inner product, let me say dash on Rn, okay, this is for n greater than 1, such that this particular norm that I have defined here, the first norm, is just the square root of V V dash. Okay. So, you cannot define an inner product such that this norm is obtainable as the square root of V with V, the inner product of V with V with respect to that inner product. Okay. So, in a sense, norms which come from inner product are very special. Okay, they are somehow related to squares. There is some sort of squares and square rooting which are inherent in their definition, and as soon as you move away from squares to other things, so for example these two things which I wrote out, there is a more general P norm, so let me call it NPV, which is you take each of them raised to some power P, and then so this for any P greater than or equal to 1. So, this is actually a more general LP norm where I just take the pth powers of all the AIs and then raise the answer to the power 1 by P. Okay, so, if P is 2, then it is our usual familiar norm or the Euclidean norm. Okay, so again this is just to say we have got norms which come from inner products and norms which do not come from inner products, and there are situations in actual applications where both these things are sometimes important. Okay, you may want to measure, so norms are a way of measuring lengths or distances, and you may have a particular way of measuring that is relevant to a particular problem. Okay, we may want to actually measure the maximum distance between two things. You want the maximum coordinate, somehow that is what is relevant to your application rather than the sum of the squares. Okay. So, these are all things which can be put into this framework of norms which may or may not come from inner products. Okay, any questions on this so far? Okay, so let's move on. Let's go back to inner products again. So, we will talk about, so back to inner products, we will set aside these more general norms for now. Okay. So, now let us talk about some computational aspects. So, what I mean by that is suppose you are trying to program a computer to sort of keep track of an inner product. So let me say it like this. So I take some vector space, I let's say I am looking at the space Rn, and suppose you are given an inner product, okay, I give you some inner product. How are you going to feed that to a computer, or how will you represent that inner product in some form on the computer, so that what would you want to do if I then give you subsequently, I give you any two vectors in Rn, you should be able to get the computer to compute the inner product of that pair of vectors v and w. Okay, so somehow you have to store this inner product there such that afterwards I give you any pair of vectors whatsoever, you should be able to tell me what their inner product is, right. So this is sometimes a what you call a data representation problem, or some kind of a storage problem. So I mean the obvious very bad way of doing it is to just keep track of all possible pairs of vectors v and w. I mean what's maybe the brutest of brute force ways of doing it is you just keep track of all these things. For every vector in your vector space, you keep track of v, w and vw. You make a big table basically, vector 1, vector 2 and inner product. So you just keep track of all these infinitely many triples, right. Of course that is not feasible because it is firstly an infinite list of data, but in a sense to be able to calculate all these VWs, I do not need to have all these infinitely many pieces of data, right. There is a much more compact storage option possible. So how much information do I need to keep track of, which information do I need to keep track of in order to be able to reconstruct the inner product for all pairs? Basis, great. So we could just start with the basis. So that is the first observation. So let us start with the standard basis of Rn. So what standard basis, I mean we could pick any basis really. So let me take v1, v2, vn, be any basis. For example, you can take the standard basis 1 0 0 0 1 0 blah blah. Okay, but of course you can choose other things as well, and for all these n guys you just keep track of all pairwise inner products, that is for all ij you figure out, you compute vi vj. I have given you the inner product in some sense, which means for these pairs I know the values. So I know what the inner product of vi with vj is, and what I do is I just form a matrix with all these numbers. Okay, here I and j go from 1 to n. So I have essentially calculated a n cross n matrix. This is some n cross n. So I said over the real numbers, you could also do same sort of thing over the complex numbers. So what I have gotten here is an n cross n real matrix. Okay. Now if firstly how many different numbers are there in this matrix? Of course vi vj is the same as vj vi because of the symmetry property, and so in a sense it is actually a symmetric matrix. It is an n cross n real matrix, in fact it is a symmetric matrix. So I really only have half the matrix number of entries, right, whatever n into n minus 1 by 2 or n plus 1 by 2. So I have those many distinct numbers possibly, and so this is very compact. I do not have infinitely many anymore, but if I have those numbers, it is enough for me to compute any other inner product, right, because now if I have v is summation ai vi, w is bj vj, then how do you compute the inner product of v with w? If you actually write the whole thing out, it is summation ai bj vi vj, right. So I have just used the properties of the inner product over all i's and j's, and this in a sense is just a simple matrix product. So this is the row vector a1 a2 an, the matrix G, column vector b1 b2 bn. So this is what you would write as v transpose g w, right. So, I think of V as the column vector, then V transpose is the corresponding row vector. So, the inner product between any two guys V and W is just a simple matrix product. I just take V transpose G W. So, in a sense all I need to do is just keep track of G alone, right. So, this is one of the first things to note, that when I have an inner product, there is this nice compact data representation that I have, which is only the matrix of inner products. So, this guy is sometimes called the Gramian matrix or the Gram matrix of the form of the inner product. Okay, this turns out to be actually much more than just real and symmetric. This is actually also positive definite matrix. Okay, in fact, any inner product can be obtained in this manner. You could start with a positive definite symmetric real matrix and define your inner product in this way as V transpose GW. Okay, in a sense, the other example of an inner product that I gave you for R2 is sort of something like this. It comes from a different positive definite Gram matrix.
You mean A transpose G?
Sorry, what?
A transpose GBA.
Yeah, okay, maybe I should have said A transpose GB instead of V transpose GW. So, this vector, okay, let us do that. So, let us call this vector as A transpose, this vector is B. Yeah, so V and W are sort of the abstract vectors there. Thank you. So, this guy is A transpose GB. Yes. Okay, so that is the data representation problem. Now, in a sense, the key relationship between these two, between the inner product and norm, is the following. So, recall yet another important relationship between the inner product and norm. This is the Cauchy-Schwarz inequality. And this just says the following: if I have a inner product space, then the modulus of the inner product is less than or equal to the product of the norms. For all vectors in my inner product space. Right. So, this is the familiar Cauchy-Schwarz inequality. Now, you can think of this as some sort of a relationship between the norms and inner products, right. It bounds the inner product in terms of the norms. And the proof itself, so I will not go fully into this, but I just want to make a remark about the proof of the Cauchy-Schwarz inequality, and it will come up again and again in what we have to say and in the applications and so on. So, the idea, if you remember how the proof goes, it is the following: we have this vector W, we have this vector V, and what we do is we sort of project V along W. So, you drop a perpendicular if you wish. So, you sort of look at this projection here of V along W. Okay, so this, let's call this vector as Z. So, Z is what we would call the projection of V onto the span of W, the one dimensional span. So, what is that, or equivalently resolve it into the component along W and sort of perpendicular to W. Now, how does one compute Z itself? So, the standard way of doing it, let me recall this for you. So, let's take the unit vector along W. So, I will write W hat to be the unit vector so unit vector along W, and once you have so I have just normalized W to have unit length. Once I have that, I just have to take Z to be the following. I will just take V inner product, this unit vector times this unit vector. right. So, this is a usual way in which we project, right. I have the unit vector along a certain direction, I just take the inner product of this vector with that unit vector multiplied by the unit vector. So, I have just now written what I get when I the component along W. Now, so consider this as Z. So, define Z if you wish as follows, to be the projection of V along W, and it is now easy to check that if you take what is left over. So, if you take this remaining guy which is V minus Z, okay, then it is easy to check the following, that V minus Z is now perpendicular to Z. Okay, so, this is the crux of the argument, that if you define Z in this clever correct manner, then what is left, which is V minus Z, will always turn out to be perpendicular to Z. Okay, so, let us just check it fast. So, what is perpendicular means V minus Z comma Z inner product should be 0. So, let us compute it. It is V comma Z minus Z comma Z, and Z has been defined in a certain manner. So, it is V comma this guy, which by definition is just V W hat. So, I will pull that out into V W hat minus Z comma Z inner product is just again the same thing, okay, and so the answer is 0, right. So, this is how the proof goes. Now, the reason I am pointing this out, so I mean let us complete it. So, beyond this it just says that I have kind of written V in, I have put it into a right angle triangle, and now if you actually calculate, so we have Pythagoras theorem which also works in the general inner product setting, norm V square therefore turns out to be norm Z square plus norm V minus Z square. Okay, why does that happen? Because V minus Z and Z are orthogonal to each other. Okay. So, I am just recalling Pythagoras theorem here in the general case, and this just means that norm V square is therefore greater than or equal to norm Z square. And that is really what Cauchy-Schwarz inequality says. Okay, so, this final thing which is Pythagoras theorem, in a sense the hypotenuse is larger than this side, translates, if you unravel it, this will give you Cauchy-Schwarz. Okay, so, let us unravel it. This just tells me that norm V square is greater than or equal to, so what is the norm of Z square? Z is this scalar times a unit vector. So, this is just norm Z square is just the norm square of the scalar itself, okay, and the norm square of the scalar, since W hat is just the unit vector, it is W by norm W, this is nothing but norm square of this divided by norm W square. Okay, so, the net result is that I can now take norm W square to the other side, and I get norm V square norm W square is greater than or equal to mod V W square, and then you take square roots to obtain the Cauchy-Schwarz inequality. So, at the end of the day, the Cauchy-Schwarz inequality is just in a sense what you get from the Pythagorean inequality, that the hypotenuse is actually larger than the side that you project onto. Okay. Now, the sort of I said this for two important reasons. The Cauchy-Schwarz inequality uses this very fundamental idea of orthogonal projection, that I have a vector, I project it onto another space, and that is going to be very, very important for all the various applications, especially in data science. That is one reason. The other is that the inequality itself is actually a very important sort of statement. It gives you very non-trivial relationships between bunches of numbers or functions or matrices and so on. For example, here is what you would get if you apply the Cauchy-Schwarz inequality to the vector space Rn with the standard inner product. So, if you take this as your inner product space, then the Cauchy-Schwarz inequality says, so what is the inner product of any two vectors. So, I take my two vectors V to be x1 x2 xn, W to be y1 y2 yn, then their inner product is summation xi yi, and the Cauchy-Schwarz inequality says that this guy is less than or equal to summation xi square summation yi square. So, this is just the usual Cauchy-Schwarz, but then here is another application. If I had two matrices A and B are both m cross n real matrices, recall we had an inner product on this space, just a standard inner product on the space of matrices, but the inner product had this very nice, I mean real or complex matrices. If I take real, it is AB transpose. So, it says the following: if I take two such matrices and I take trace of AB transpose, the square of that is at most trace of AA transpose times trace of BB transpose, right. Likewise, I could do this for star, trace of AA star trace of BB star is greater than or equal to trace of AB star the whole square. Any questions on this? How is it clear how I got this? All I have done is just applied the Cauchy-Schwarz inequality to a particular inner product space. Okay, which inner product space? The space of all m cross n real matrices with what is my inner product? The one that we talked about earlier. If I take AB, then just standard inner product can be just written like this. Okay. So, this is actually a a strange, at least on first glance, a strange looking statement about traces of products of matrices in some form, but it is actually just the Cauchy-Schwarz inequality. Likewise, it says that if I have functions f and g, then if I integrate the product, so this is for real valued continuous functions, maybe I will take complex. If I have complex valued continuous functions, then it says that this is less than or equal to so it is now a statement about functions and integrals. And for what? For all f g continuous complex valued functions on 0 1. Okay. So, in a sense I have written down three statements, one about real numbers, one about matrices, one about functions, but all of them are actually just the Cauchy-Schwarz inequality applied to different vector spaces with different inner products. Okay. So, this sort of thing is very important when we have this is part of the justification for why we study inner product spaces in an abstract setting, because once you prove statements like Cauchy-Schwarz and other things abstractly, then the applications are usually amazing. We can apply them to very diverse sort of things to get very strange looking formulas which you couldn't possibly justify if you just thought of them as functions separately, or I mean it would be a royal pain to try and prove this last inequality, for example, just working with functions, right. So, it is easier when you place it in this other broader context. Okay. So, that was my other motivation for talking about the Cauchy-Schwarz itself, and there are generalizations or sort of strengthenings of Cauchy-Schwarz which come up in all kinds of places in Fourier analysis, also in the data science applications that are mentioned in the book, for example, in image sort of image manipulation and so on. Okay. I am hoping Pranabendu will talk a little bit more about some of these applications. Okay. So, let me move on to the next thing, which is the notion of orthogonality and orthonormality. So, let me recall the standard things here, again things which I am sure are familiar, but this is sort of where the heart of this whole subject starts. So, what is orthogonality? So, we have already seen what orthogonality means. So, the definition is, if I have an inner product space, then you say that two vectors are orthogonal if their inner product is 0. So, that is the first definition, and a subset of V is orthonormal, and we could also define orthogonal, but we go straight to orthonormal if the following happens: every vector in that set has norm 1. So, that is what normality means, and every pair of distinct vectors is 0, has 0 net product or is perpendicular. So, this is what an orthonormal set is, okay. And the standard, I mean, this is somehow the key sort of notion in many applications, that of an orthonormal set. The key fact, which again should be familiar, is that if I have an orthonormal set, then it is automatically linearly independent. So, let me abbreviate orthonormal set to ONS, then S is linearly independent. Right. So, this is one of the standard things that we know about orthonormal sets. Again, proof is just one line. So, if you recall how it goes, if S has a bunch of elements E1, E2, Ek, and to show linear independence, if a linear combination is 0, all you have to do is just take inner product on both sides with Ej's, then take the left hand side, inner product with Ej should equal the right hand side, which is 0, inner product Ej. But because of orthonormality, every pair has inner product 0 and only Ej will give you inner product 1. So, this will pick out exactly the jth coefficient Cj, right. So, this is how the usual proof goes. So, orthonormal sets are automatically linearly independent, mainly because you can pick out any chosen coefficient. So, if this is the coefficient you are interested in, it can be picked out in this manner just by taking inner product with a particular Ej, right. So, this is the key thing that comes up here. Okay. Now, so orthonormal sets are really the main ingredients that you need to define the next object of interest, and these are now. So, I am going to talk about two different algorithms or two notions. So, there are two things, as I said. So, one of them is called orthogonal projection. Okay. So, this is, we have already seen a version of it in the case of the Cauchy-Schwarz inequality, but here is a more general version. I have a subspace W in my vector space, I have got a vector V in my vector space, and the orthogonal projection problem says find a vector W, sort of drop a perpendicular. So, find a vector W in your vector space W such that V minus W is orthogonal to that entire subspace W. Okay. So, orthogonal projection is the following question. Let me say orthogonal projection algorithm. It has the following input: a subspace W and a vector V in V. What is the desired output? Is a vector W in W satisfying the following property, that V minus W is perpendicular to every element of W. Right. So, this is what the orthogonal projection algorithm asks for. I give you a subspace, I give you a vector as input, the output you should give me is the point W in W with the property that the difference, so that is the the vertical thing there, the V minus W bit is normal to this subspace, right, it is perpendicular to every vector of the subspace. So, that is what we want to do. Okay. So, let us solve this problem. So, this W that we have is called the orthogonal projection of V onto the subspace W. So, how do we do this algorithm? How do we solve this problem? Any suggestions on how we could do this? So, I need to be given W in some form, right. When I say I give you a subspace W, what do I actually give you?
The basis of W.
Let us say I give you a basis, but let us even say I give you something better, I give you an orthonormal basis of W. Suppose I say input is not just W subspace of V, but also say an orthonormal basis S of the subspace W of V. Okay. So, for W I give you an orthonormal basis. So, if I give you that, then can we do this? Okay. So, let us see how we would do this. So, let us call that subspace, let us call that orthonormal basis something E1 E2 Ek. So, this is given. So, what is it that we want? We want to find this W, right. So, I am also given my vector V. What I want is my W. But what property does W satisfy? W satisfies this property such that V minus W is perpendicular to every x. And perpendicular to every x is the same as saying it is perpendicular to every one of the EIs. Right, that is enough, because EIs form a basis of the space. To say its inner product is 0 with every vector of the space, it is enough to ensure it is 0 with every basis element, in fact orthonormal basis here. But let me try and ensure this. I want to find a W satisfying this property for all I equals 1 through k. Okay. Now, that gives me an equation, right, that gives me a bunch of equations in fact. So, what does it tell me? It tells me that, so this equation says V inner product EI is the same as W inner product EI for all I. Okay. So, what is W therefore? So, I remember I know something else also, W should come from W, it is not some random vector, it is a vector from the subspace, right. So, if W comes from the subspace, then I also know something else about W, right. What do I know about W? It is a linear combination of the EIs again. So, I really have in a sense to determine these constant CIs, I just have to find those coefficients, because I know W is coming from W, it is a linear combination of the EIs. But then W is also having this special property that V minus W is orthogonal to W. In other words, I get a bunch of equations which W must satisfy, right, these equations. So, now I am in business, because if W is summation Ci Ei, what is W Ei? It is just Ci, right, we just use that argument. That is the advantage of having orthonormal bases. If you take inner product, you will only get just that one coefficient alone. So, therefore, we have done what we needed to do. Therefore, here is the algorithm, or here is the prescription. I just define Ci like this. I know my V's, I know my EIs. So, I can compute my inner product of V with EI, right, it is some number. Those numbers are my coefficients Ci that I put into W. So, define Ci like this, and take W to just be summation Ci Ei. In other words, W is just this guy. Okay, and observe just everything we have done so far sort of says W is unique, right? There is only one possible thing that can happen, because we started out assuming W has this form, and then we said W must satisfy some equations, and the solution was only this one possibility, Ci had to be this number, right. So, there is really only one solution, W equals this, and we must check that it is actually a solution, right, which it is. I mean, in a sense you just run your arguments backwards, you will see that W will of course satisfy these equations. Okay, so in fact there is a unique solution to this. See, a priori when I started out I did not know that, I know that, see what did I ask for, I said input I give you all this, output I want to find at least one W which has this property, but it turns out when we did the analysis that W is unique, there can only be one possible W, and that W is exactly the one that is given by this formula below, summation V Ei Ei. Okay. So, this vector is called the orthogonal projection, because in effect what we have done is the following: we have really decomposed V into two pieces, right. We have resolved V along this subspace and perpendicular to this subspace. So, given V, we have found this vector W and this other vector Z. And what is this other vector Z? Z is just V minus W, that I called V minus W, right. So, define Z as V minus W. So, then what we have done is really written V as two pieces. V has been decomposed as W and Z, W coming from W, and Z, what is Z? Z is a very particular kind of guy. Z is perpendicular to everything in W. Let me write it like this: Z is perpendicular to the subspace W, right. So, I have decomposed into two parts, and W is called the orthogonal projection of V. So, let us give that a name. W is called orthogonal projection of V onto the subspace W. Okay. So, this is an important construction, and what we have seen is that it is actually very easy to carry out. If you know the orthonormal basis of the subspace, you can actually figure out what the orthogonal projection onto the subspace is very easily. Is okay? Okay. Now, let me ask for another computational problem. Here is a slightly differently framed question. So, this problem was the orthogonal projection algorithm. Okay. Now, there is a similar algorithm, I mean there is a analogous question. So, let me call this the closest point algorithm. So, the closest point, yeah.
Sir, what is the intuition behind it, sir, the orthogonal projection?
What is the intuition is exactly what we did in that Cauchy-Schwarz, right. That is, we want to find a point which is, see, if you are in one dimension, I mean if both these are, imagine you are in R2. So, R2 we do this all the time, right. So, we have got one vector, we sort of drop a perpendicular to this line, and then what you have is you write it into these two pieces, one which is along and one which is perpendicular. Like vectors, we always resolve it along the 3 coordinate axes and so on, right. One component along I, j, k, etc. So, that is exactly what we are doing here. We are resolving it along this direction W and some portion which is perpendicular to W. So, those are the two separate parts that you are doing. Is it all right? So, that is one intuition, but I am going to give you another one. Okay. So, here is a slightly different problem which is also very natural, which is the following. I have a vector space V or an inner product space V, and I have a subspace W. Okay. So, I have got a vector V, I have got a point V here. Now, I am going to ask for the following: remember I have an inner product space, so in fact I also have a norm on this space, okay. But actually the closest point algorithm, that question can be asked in any normed linear space, not necessarily in an inner product space. See, orthogonal projection, this problem on the left that I have just defined, this, for this I have to assume that my vector space V is a inner product space, that is my starting data, okay. So I should say V comma bracket is an inner product space. Now closest point algorithm, actually I only need to have a notion of a norm in order to state the problem. In order to solve it, of course I am going to do it only in the case when there is an inner product. So to state the problem, imagine that my vector space has some norm, it is a normed linear space. So the question says, given a vector V, find a vector W in this space such that W is closest to V. Okay, now what does closest mean? So okay, I want, so input is the same thing. It's just a subspace W of V, vector V in V, and the desired output is a point, it could be more than one point also if possible, a W in W such that W is closest means shortest distance possible, it is closest to V among vectors in W. Okay, among all possible vectors in W, I want to find the fellow which is the closest possible guy to V. Okay. What does that mean? How do I rewrite it in terms of norm? In other words, I want norm of V minus W. See, this is the distance of that vector, this is the length of that vector. Norm of V minus W should be less than or equal to norm of V minus X for all X in W. Okay. So this is how you formulate that question. It has got to be closer, W is closer to V than any other X. So if you take distance from W to any other X, it will be more than the distance to W. Okay. So I can formulate this question just with norms, but if I have an inner product, so if this norm comes from an inner product, then we will actually solve this problem. Okay. So let us see how you would find the closest point, assuming that this norm actually comes from an inner product. So let me assume something a bit stronger, that I am not just in a norm linear space, that I am also again in an inner product space, and the norm I am talking about is the norm that comes from the inner product. Okay. In this question, in this setup, what is the answer to this question? How do I find this W? It will be the same answer, it is still the projection. So the solution to the first problem is actually a solution to the second problem. Okay. Let us see why. Suppose W is this orthogonal projection, I claim that W is actually closer than any other vector on the space. Okay. So this guy is so this is V minus W. Now let us take any other, let us take any other X. Okay. So I have got this sort of pink vector, there is a red vector, and let us just join them together by this green guy. Okay. Now observe that W is actually, I mean remember this normal, this guy here is actually normal to every vector on my space. In other words, that triangle which I have drawn there is actually a right angle triangle, right. That V minus W, so what are the three sides of that triangle? I have got this one side, so let us draw this again. So this is V minus W, this fellow is V minus X, and the third side is X minus W. Observe that X minus W is actually what? It is a difference of two elements of W, right. So X minus W lies on W, it's on the subspace. And what was the special property of W? Its property was V minus W, this guy which is sticking out, is perpendicular to everything in W, right. So if you actually look at it here, V minus W is orthogonal to W. So let us write this out. So if W is the orthogonal projection of V onto W, then I have got this right angle triangle here, V minus W, V minus X, X minus W. So observe V minus W is orthogonal to X minus W, okay. And so by just the Pythagoras theorem again applied to this case, it says norm of V minus X square is norm of X minus W square. In other words, norm of V minus X square is definitely more than norm of V minus W square, right. So the hypotenuse is definitely larger than this side, and that is all we claim, right. We claim that this W fellow is closest to V, its distance is actually smaller than the distance between V and any other point on the space. So this is sort of our usual intuition, right, that when I have a subspace, I have a point outside it. What is the point on the subspace that is closest to this point? You just drop a perpendicular, and that is all we are saying here in the context of inner product spaces. So this is the other intuition behind orthogonal projection. It actually solves the closest point problem also. It allows you to find the point that is nearest. Okay, so orthogonal projection and closest point, they both have the same answer, and the thing here is, see, the closest point approximation is actually something that appears in the other familiar guise of what is called the least squares approximation. So if you see what I have here, see, when I say norm of V minus W is smaller than norm of V minus X, let us also square both sides. Norm square of V minus W is less than or equal to norm square of V minus X. So what this says, if you do it in the case of Rn, right, is you are asking for a point which minimizes. So what does the norm square mean? It is just the sum of the squares of the differences of the coordinates, right. So let me just rephrase this closest point in terms of a more familiar formulation. So the closest point thing says, so given W subspace of V and given a vector V in V, so let us say V is some A1 it kind of says find W, so I'll call it W1, find this to be, okay, find x1 x2, such that the sum of the squares maybe I should call it W's, sorry, just a second. So let us call the coordinates of W as W. So I want to find n numbers, so I am given n numbers A1, A2, An, and I want to find n numbers W1, W2, Wn such that that vector will lie in the given subspace W. So there is a certain constraint that this tuple W1, W2, Wn must come from W. I want to find these guys such that summation Ai minus Wi squared is less than or equal to sum of Ai minus Xi squared for all tuples x1, x2, xn which come from W, right. So I have just rephrased my problem of finding the closest point where my vector space V is now taken to be Rn or Cn, okay, because a norm there is this standard norm, right, it is just sum of the squares of the coordinates. So this is like the usual, what we call the least squares approximation. In a sense, I have this tuple A1 A2 An and I am trying to search in this search space. I have got the space W in which I am trying to search for my best approximation, such that it minimizes the difference, the squares of the sum of the squares of the differences, right. So this is, if you think of this as some kind of error between the original, the AI and the Wi, you are sort of trying to minimize that error, trying to find the thing which makes that the smallest possible among all possible choices of x's which come from that subspace. So this is usually, these sorts of things are what you call least squares approximations. So that is nothing but this much simpler, give me a lot of grief. So that is just this basic problem of trying to find the orthogonal projection, okay, and the orthogonal projection problem itself has a very quick solution, it can be solved very fast, okay. So that's an aspect which I haven't yet talked about too much. See, all of this is finally about trying to implement it, for example, on a computer, or how easy it is to compute and so on. So the problem formulation here is kind of tough, right. I am saying I have to search in this space W such that this least square error is the least possible and so on, but the point to note here is that the solution itself is very quickly computable. Why? Because we have converted this problem into the simpler problem of just performing an orthogonal projection, right. We have changed problem number 2 into problem number 1, and orthogonal projection is just a simple linear algebra problem. What does it say? Your final answer, the projection, is just given by a simple formula. You should just be able to calculate all the VEI's and just take that into EI, right. The solution comes in sort of 1 second.
So we need to calculate EIs first, then
We need,
can do the perform this algorithm.
correct. So we need to have the EI's. So that's the only drawback.
The costliest part will be part.
That will be the costliest part, right. So at this point, so it's a very important point here. All along I am saying you are given a W, right. I am given a W and I want you to perform this. The point is, how are you given a W? What does it mean to be given a W? So there I made an assumption here. I said, let us assume you are given an orthonormal basis of W. If you are given that, then doing it is very quick, it is very cheap. You can just plug into this formula and you are done. But in practice, you are not usually given an orthonormal basis of W, okay. You are just given, for example, maybe some spanning set of W. How is W specified? How is it given to you? It is just given as, here take this list of vectors, W is the span of this list of vectors, or maybe you are given just an ordinary basis, not an orthonormal basis, okay. And then the question is, okay, here is W, it is a span of this basis, now do this algorithm, trying to find the closest point, okay. So in all those cases, the first step somehow is finding an orthonormal basis from the given set or from the given basis, right, and that's sort of where we will start tomorrow. So that's what is usually called the Gram-Schmidt orthogonalization process. Okay, we will stop here.